Hello, everyone. Thank you very much for being patient. It's a real pleasure to be back here. It started. We're officially going. And so I'm sorry for the delay. Actually, as some of you know, I've been working on trying to fight COVID-19 with an app called Novid. And I was just on a call with some of the leadership of a hospital organization. So sorry about that. We're just trying to do a few things to try to make the world a more healthy place. Great. Yes, and thank you very much for being patient. I mean, I really am amazed that people are still here, but I want you to know one thing. It is actually very important to me to actually make sure that we do this YouTube live stream every day. So, I will get here. I will get here. I didn't forget all of you. Okay. Great. So now let's see. I should first of all give a little welcome to anyone who is new, for anyone who's here for the first time. You're about to see something which is completely different from what you're used to seeing in a math class. And that's called not a math class. So what I do is I like to look at the kinds of questions that people ask, and I'll improvisationally come up with something that might have some math in it might have some science in it, might have something to do with the real world. But ultimately, it will be understandable to people who are taking algebra or geometry. If you want to ask more sophisticated questions, harder questions, those will be for other live streams. Actually, if you were interested in something called matrices, there's a YouTube video from last night where I was doing something with 200 math teachers in New York. But for here, let's see, what kind of questions can we talk about today? I'm going to look and see what we have here. Oh my gosh, somebody already said calculation of 4x4 matrices. So if you're interested in matrices, as I said, last night there was an entire session that was talking about matrices. Just go and check on this YouTube channel and look at the one that went out last night to Math for America. You'll see some stuff about matrices. What other questions do we have here? Oh, okay. Oh, this is interesting. So Min Ko has asked the question, is there a strategy to rock, paper, scissors? Or is it a totally random game? That's a good question. Okay, so rock, paper, scissors is a simple game where somehow you can either put rock or paper or... Wait, no, that's not paper. Rock or paper or scissors, right? And the basic principle is that somehow for each of those plays, there's something that beats it and something that's beaten by it. So then, is there a strategy? Well, I can tell you one thing. I have a strategy for rock, paper, scissors where your chance of beating me is exactly 1/2. And my chance of winning is also exactly 1/2. It's a completely fair game. My strategy is very simple. All I do is that at every moment, I randomly will pick one of the 3 options, and with a probability exactly 1/3, I'll pick each option. And I'll do it independently of you. So that's a very important word. So that we are playing rock, paper, scissors. Now when you play rock, paper, scissors, my strategy is going to be like this. I don't care about you, I'm going to pretend you don't exist, and with exactly 1/3 chance, I choose each of those. So I'm going to choose each one with a 1/3 chance, 1/3 chance, and 1/3 chance, independently of you. The word independently is very important. It means that no matter what fancy strategy you have, I'll still have a 1/3 chance of each of those. So then the way you can analyze this is you can use something called conditional probability. That's a fancy word. Another way to think of it is, well, let's pretend that, even though, not let's pretend. Since it's independent, it doesn't matter, what your strategy is. If your strategy is going to give me a rock, I still have a 1/3 chance of tying with you. By the way, when I say a 1/2 chance of beating you, what I mean is if there's a tie, do it again, right? Until there's a result. But like no matter what you were going to present, it's like you present the rock. Well, I have a 1/2 chance of beating it. Oh, sorry, I have a 1/3 chance of tying, which means we do again. 1/2 chance of beating and 1/2 chance of getting beaten, and it's all exactly the same chance of winning or losing, and that's guaranteed by this independence. Now, there's something very important about the word independence. Independence means I really don't care what you did. It will still be this probability. Because of independence, the way you analyze this is you could even pretend that what happened is that first the other person showed you what they had and you just ignored it. And you said, okay, great, I still will randomly pick 1/3, 1/3, 1/3, and that's how you know it's an even chance of winning. Why did I dwell on that? It's because there are other ways to pick that aren't independent. Like what if the way that you picked is you said, I'll try to, I want one third, one third, one third. And here's how I can do one third, one third, one third. Here's the best strategy in the world. It's going to be one third, one third, one third. Watch. This is the super secret strategy. SSS. The super secret strategy is you go rock, and then you go paper, and then you go scissors. Then you go rock, and then you go paper, and then you go scissors. And then you go rock, and then you go paper, and you go scissors. Who likes my strategy? I mean, this is a pretty good strategy. You have a 1/3 chance of each of them, right? It's like if I just go rock, paper, scissors, rock, paper, scissors, rock, paper, scissors, then indeed, like after a while, it's going to be like a 1/3 chance of a rock, 1/3 chance of a paper, 1/3 chance of a scissors. But somehow someone thinks it doesn't look random. Actually, some people say like, look, if you saw someone doing this, then you could even win all the time, right? So the problem is that there's this notion of like dependence, independence, randomness or not randomness. Like I could actually pretend that this was random in the sense that if I'm only going to play once, like if I'm only going to play once with you, how do you know where I am in this sequence anyway, right? It's just that you don't know. I might be somewhere in the sequence and from playing against someone else. But the issue is that this is something that has a lot of dependence inside it. It's not really like a 1/3 chance of each of those. So what I'm trying to say is there's a huge advantage to going and saying, I will make something completely random and completely independent of you. It makes the analysis clean. I want to tell you a story about this. So a lot of times when people do some game like this, they try to psych out the other person. You try to be like, well, you just did 2 rocks in a row. So if you see 2 rocks in a row from the other person, clearly the next thing that they're going to play is a scissors, right? Because if they did 2 rocks in a row, they're trying to psych you out. They want to make you think the third one's going to be a rock so that you will play a paper, and that's why they play a scissors instead, and the scissors wins. Okay, but you see, somehow that's not really that solid, because how do you know? Maybe they were psyching you out on that in one more level. So with these kind of strategies, if you're just always trying to use some kind of psychology, it's not really clear that there would be a way that always works. On the other hand, this is guaranteed that you will never have a chance of winning or losing that's any different from 1/2. That said, I can tell you that I've used something like this before. A long time ago, when I was still a student, I once played in some of these, like there was some stock trading contest. You could just go and you buy some stocks and sell some stocks with fake money. It wasn't really your money. And you go and see who wins the most money. And so what I did is I ultimately I came up with a strategy that I knew would either win a huge amount of money, the strategy would either earn a huge amount of money or lose a huge amount of money. And with this kind of a game that I was playing, the stock market game, the way it worked is you didn't use your real money, but whoever got the most earnings would win a real prize. It's like a real prize, a real money prize. So here's what I did. I flipped a coin. I actually flipped a coin. And by flipping a coin, I was able to decide whether I wanted to bet that the market would keep going up or bet that the market would keep going down. You're apparently able to do both of these. And by flipping the coin, I knew I had a 50% chance of actually trying to, potentially winning this entire contest. So that's just showing you, like, you don't really want to let any bias come in. The best is to go and do something completely random. Let me also tell you where you can do something completely random. If you really want a random number, don't do it by asking your computer, because your computer, don't use your computer's programmatic random number generator, because it doesn't. The numbers sort of depend on the previous ones. Not as bad as this, but they do depend. On the other hand, what you can do is that you can go to random.org. And random.org is a website that lets you generate random numbers that I think are, I don't remember exactly, but I think it's using things like atmospheric conditions and like things that are actually physically random. So that is actually where I got my coins when I was trying to flip to decide what to do in that stock trading contest. Yes, somebody made the comment pseudo-random. Pseudo-random is exactly what it is like if you use just your normal computer's random number generator. Okay, what else can we do here? Oh, you know what? I should tell you one more thing. Believe it or not, there is actually a rock, paper, scissors tournament. And the reason is because most people who are playing don't do this. In fact, it is very, very hard for a human being to really generate a random number. And so people who maybe study more about psychology go and try to find ways to exploit the fact that humans aren't really able to make random numbers. That is exactly why what I chose to do is I chose to go to random.org to generate that coin flip when I needed it. Okay, what else do we have here? Oh, This is cute. Tia Wang asks, who is the smartest person in the world? So it turns out that you can't really rate everyone by smartness. You can't just go and say, there's this line, and how smart are you is somewhere on this line. I think the best way to think of this is that people have lots of different skills. And in fact, as I got later in life, I mean, I'm not necessarily that late in life yet, but as I kind of experienced more things in my life, I started to really appreciate people who aren't what you normally classify as smart. I mean, they might not be the kind of people who got great grades in school. On the other hand, they have lots of amazing skills. So I've come to learn that there are some people who have really, really interesting skills, and sometimes they might not rank highly on this smart scale, but if you want to do something interesting with them, or you want to work on some major project, they might be the right people for the job. So I don't think that I can tell you that there is a smartest person in the world. All I want to tell you is, appreciate all of the other skills that you see in anyone else, and you yourself try to develop all kinds of these skills, because there's not only one that's important. Not even just math. Okay. Mike Bobby. What is the most mathematical board game? So I guess to me, if I was going to talk about a mathematical game, I might not talk about a board game, but it's similar to that. And maybe some of you have seen this thing before. Maybe that I don't want to talk about that then. Some of you will have seen it before. The game's called NIM, N-I-M. If you're curious at all about this and you want to go and pull a trick on other people, just go search Google for NIM, N-I-M. And actually, please don't pull a trick on other people. That's not nice. If you want to know other games that maybe are mathematical, I once saw some board game which was involving where you have to prime factorize stuff. And that was kind of interesting. There was some board game where somehow you could move to a certain square by multiplying or something like that. And that was quite cute. Like you somehow these prime number squares you can't get to. Thought that was interesting too. Although if I think about board games, some of you know that Monopoly, Toady Master has said it. I've given a lot of these talks about how you can use math to do better in Monopoly. Actually, I'll tell you one thing about Monopoly that's mathematical. Do you know which square in Monopoly, or which squares in Monopoly, are the most commonly landed on? There's actually one square in Monopoly that is the most commonly landed on square. Does anyone know what that is? Which one square in Monopoly is the one that you land on the most? Jail. Vincent Wang? Exactly, it's jail. And the reason it's jail is because you can get to jail in lots of ways. You can get to jail by walking on this go to jail. I see somebody said starting square. Starting square is also common for another reason, but at the same time, jail is more common because of how many ways you can get there. There's a square that says go to jail, and then you go to jail. There's another way to get to jail by using those orange cards, the chance cards, and then I think, is that true? Is there an orange card that sends you to jail? I think so. Is there a yellow one that sends you to jail also? I haven't played Monopoly in too long. There might be one that sends you to jail from the yellow. And certainly you can also, 3 doubles, thank you David Xiang, that's right. Rolling double, the same number 3 times in a row, then you also go to jail. And there's also another way to go to jail, by just walking onto the jail, and that's called just visiting. However, because jail is so common, if you want to know what, there's some colorful properties, like the streets or whatever. If you buy 3 of them, then you can build some hotels. In fact, the area that's landed on the most is the one that's about 7 squares after jail. Why? It's because they get to jail, and then when they get out, they kind of just walk, and 7 is the most common number. Numbers around 7 are the most common, and so they go there. Somebody said buy jail. Indeed, I guess if you could buy jail, that would be pretty good. The only problem is in Monopoly, you can't buy jail. So what you want to buy is you want to buy the stuff that's 7 squares after jail. That's pretty good. Another interesting thing about Monopoly is that it seems to me, I don't know if you guys have this version, but it seems to me that somehow the new versions of Monopoly don't even use paper money. I don't know if you have this, but I saw some kids playing a Monopoly game where they used ATM cards. It was somehow some cards with chips, and you put the cards in, and it was bank cards. To me, when I looked at that, I thought, oh no. I thought the whole point of Monopoly was to teach people how to make change, not to use these bank cards. But anyway, okay, let's see. What other questions can we do? Ultimate banking with credit cards. Yes, actually that is true. If you use real credit card ideas, then Monopoly will be really weird because credit cards let you have negative money. Okay, let's see. What else do we have? Oh, somebody has the credit card Monopoly. So John Liu, I wasn't making this up. This is a real thing. I also noticed that the Monopoly, the numbers on Monopoly got bigger. It used to be that it was everything was in the hundreds, but I saw that somebody added like 3 more zeros or something. Okay, what else can we do here? I'm looking here to I also have some questions which are coming over on this side. Ah, Immortal Banana, you have a really interesting username. You asked, how is our number generator really random? And that's a good question. It's because if the number really just comes from, a sequence of numbers, well, it's not random. It's just like how this is not random at all. On the other hand, some people try to use things like atmospheric noise to try to generate something that's random by saying, we believe that the way that the physics of the world works uses something called quantum mechanics. And people believe that in quantum mechanics, some things are randomly done. And so things that are in nature could actually be random. This is related to these like Schrodinger's cat stuff that people sometimes are posting into this chat. But in any case, if you use real physical things, then you could potentially get something that's random. So that's, I believe, what random.org uses. More questions. Oh, David Tiang asked, strategy for winning tic-tac-toe. So it looks like today our focus is on game theory, which is totally fine with me. Do you know the strategy for winning tic-tac-toe? So now tic-tac-toe is a really boring game. The reason tic-tac-toe is a really boring game is if you know what you're doing and you move first, you can guarantee that you will never lose. Oh, somebody asked, why do you always drink tea? Actually, it's water. I just drink the water because in this period of time when people are potentially sick, it is actually the best to try to keep your throat a little bit moist because that protects you against microbes coming in. At least that's what I had heard. Or supposedly what I heard is that it helps to wash the microbes into your stomach, where your stomach acid will just destroy them. Okay, but now let's see. Tic-tac-toe, right? I thought a lot about tic-tac-toe because a long time ago, I was actually writing a lot of computer programs, and at some point I did the terrible, terrible thing of writing a computer program to win tic-tac-toe, except that I wrote the whole computer program with if statements. I was really dumb. I mean, I wrote like 2,000 lines of if statements. I obviously had nothing better to do, and I don't recommend that. That is not the right way to make an artificial intelligence for tic-tac-toe. But here's what you can do. If you're playing tic-tac-toe, how can you think about this? The way if you wanted to think about tic-tac-toe is if you get to go first, you would just go and put it in the middle, right? And now the important thing is just to know that if you go first and put it in the middle, now there's really only 2 other kinds of games that get played. One kind of game that gets played is where the other person goes in the corner. The other kind of game that's played, the other kind of game that's played is where the other person goes not in the corner. Now I'm already showing you how to do what we call case analysis. You see, if you go and try to say, I'm going to draw all the possibilities, you'll draw forever. On the other hand, like there's really only 2 kinds of games, and then you can start using symmetry. And I see that Philip Neller already knows that this one starting on the side is bad. If you start on the side, it's bad. Why is it bad? Oh, I haven't done this in so long. So if you start in the side, like what can the x do? So sorry, if the x goes in the middle and the O goes on the side, then unfortunately the x can do something pretty dangerous. What was it? So let me see. So it's been a while since I thought about this, but I guess we'll look at the cases, right? Like how could the x potentially get 3 in a row? I suppose the x could get 3 in a row by putting corner. Right? You can win. I mean, the important thing here is that you can win. Watch. X goes in the corner. If X goes in the corner, O is forced. O is forced to block it, right? Or else O is dead. So O blocks it. Oh no! Okay, now what does X do? Oh, X does this. Boom! It's over. If X does this, then it's a double attack. Tia Wang says, then put it in the corner, then do a double attack. You put it here, then somehow, unfortunately, O can't answer. It's over. So this is how you win a tic-tac-toe. You go in the middle, and then you just hope that the other person goes on the side. And if they go on the side, oh no, says Philip Neller, and you just put that there, and it's over. Over here, it just becomes a tie. Like if this happens, like there's just nothing really interesting for you to do. There's no way to guarantee a win if O is smart. I mean, what would I do? I mean, if I was really playing this way, I would probably be like, okay, let me just force O to do some stuff. Because it turns out that if you analyze the heck out of this, if you analyze this all the way down, you cannot win out of this. So, maybe you go here, and then O is going to block you. O is not dumb. Block you. And then you say, okay, well, let me go over here and block block that possibility. You always want to make it so that O can't do this kind of double attack on you. You go there, but you notice what is so interesting. If you're the first player on tic-tac-toe, then you actually have what's called initiative. Whatever you do forces O to respond. And that way you can just force O to go in places that are not dangerous to you. I mean, at this point, if I look at the board, I say, how could O win? There's only one way left for O to win, which is to go across the bottom. Okay, I'll just block that. And I'll hope that O doesn't notice that O should go there. Oh, but come on, O will notice. And at the end of the game, it's over, and it's a draw. So I've just talked through the tic-tac-toe, and this is how you can see, this way you can get a win, this way you don't get a win. If you're ever playing O, just play O on the corner, and then you'll be able to like just counteract what X does, and you'll never lose. But that's tic-tac-toe for you. And this is also showing you how you think about game theory. You ultimately want to find out how to find the, by symmetry, to reduce the number of different cases you need to look at. And so one case is the one where O starts in the corner, one is where O starts on the side. Okay. More questions. What can we do here? Oh, interesting. So somebody put a question saying, is this true? Square root of minus x equals to I. I'm not sure exactly what your question is, so I'm going to write it down. And maybe I'll look at it, and hopefully we find out something. You're doing this. And presumably you wanted to know what is x. I mean, in that kind of an equation, here's what I would do. I'd say, I want to know what x's satisfy this. So I guess if the square root of it was I, then any x that satisfies it, I could square both of those sides, and any x that satisfies this better satisfy minus x equals I squared, which is minus 1. And if that's the case, any x that satisfies this satisfies that, and so x equals 1. Notice the way I said this. I said any x that works here works there, and then works there. But I still need to, at the end, double check that this one actually worked in the beginning. All I said so far is, if there's any x that works here, then it's 1. But how do I know there's any one that works at all? So now I try 1, put it there, and it's like, yeah, it works. So it's okay, the answer is 1, I guess. So I'm not exactly sure what was the question about, but it still gave me a chance to talk this thing through of, when you square both sides, whenever you square both sides, always plug in the answer at the end. Actually, that's what I want to dwell on a little bit here, because there are some people who are taking algebra, and you might wonder, why do I need to plug in the answer at the end? And that's because whenever you write equations, and then you square both sides, and then you keep going, what's really going on is you're saying, any x that makes this true also makes this true. And this too. You see, whenever I write equations and I go down and I say I square both sides, it's like whatever the x's are, I don't know if there are any that make this true, but if there were, I could then square both sides, and whenever I have something equals something, of course the square of the first thing, of course equals the square of the second thing, and I go down. But unfortunately, I don't yet know that this worked in the first one. I just know that any one that worked has to satisfy x equals 1. Then you try it, and it works. You plug it in at the end. So just please remember, whenever you're doing any question that involves squaring both sides or solving a quadratic equation, make sure you plug in at the end. And oftentimes that's where you find out things like, oh, so that means that the length of the rectangle is either 27 or minus 4. And you say, well, can't be minus 4, because you can't have a negative length of a rectangle. Okay, what else can we do? Oh, I see somebody has a question. Roderick Ma asks, how to win lottery. So it looks like we're playing all these like game theory and probability today. So I'll tell you, there is actually a way to, well, there used to be a way to win money on the lottery. In fact, a person who I was roommates with a long, long time ago, when I was doing math contests, he found a way to win the lottery in Massachusetts when he was a college student. And here's what happened. I don't know if you've ever noticed, but in some lotteries, there's like a prize. And then if nobody claims the prize, then you know what happens next week? Do you guys know what happens? Like, suppose there's some kind of a jackpot and nobody wins it. What happens the next week? Does anyone know? So it's like, yes, this is like some huge jackpot, but nobody got it. And then the next week, it actually goes up. So it gets bigger, it gets bigger. In some lotteries, if there's nobody who claims the prize, then it gets bigger and it gets bigger. Now you see, sometimes it actually makes sense. You know, like one thing that's worth knowing, almost always, lottery does not make sense. And you should not do the lottery. Why? Because if you do the lottery, it's like this. Suppose the lottery is something where you can win $1 million. These are US dollars, so I'll write the US dollar sign. Win $1 million. Sounds fantastic, but you go and say, with what probability? With probability, let's make some numbers that are easy. 1 over, I want like a billion. Well, a billion is too small. Let's do 10 million. 1 over 10 million. So 10 million. And all you have to do is just pay $1. Is this a good deal? What do you think? Is this a good deal? If somebody tells you you could win $1 million, the probability that you'll win the $1 million is 1 over 10 million. And all you have to do is pay $1. Why is this not a good deal? I see some people say, no, it's a bad deal. It's a bad deal because it's like somehow, on average, how would this work? There's this notion of expected value. It's like, well, okay, suppose I played this 10 million times. If I played this 10 million times, I would win on average once. So I played 10 million times, I win once. That means I win $1 million. I win $1 million. Unfortunately, I paid 10 million times $1. So unfortunately, I paid more than I made. And so the way you think about it is you use, yeah, exactly. You're giving them 90 cents. Have you ever wondered why people run lotteries? It's not because they're trying to be nice. It's because they're just making all these like 90 cents off of people. Okay? So when you look at something like this is a bad deal. Because if you look at this, it's like, the way you think of it is that how much money will you earn? Well, if you win $1 million with probability 1 over 10 million, that's sort of like winning $1 million divided by $10 million every time on average. So the way you think of this is that it's actually called the expected value, but you can even think of it on average. Expected value of winning is, actually let me call it expected value of winnings, because it's like how much money you've earned. Of winnings is the $1 million times the probability that you'll win it, 1 over 10 million, which unfortunately is just 10 cents. Bad deal. It costs you $1. So now let me give you a different situation. This is a bad lottery. But you know, what if nobody claims the jackpot? If nobody claims the jackpot, then what if it becomes like $2 million or $3 million? There is a point where it breaks even, right? Like what I'm trying to say is that in some lotteries, it's not so bad. It's not like it's 10 to 1. It's not 1/10 of the chance. Sorry. It's not like the expected value is 1/10 of the cost of the ticket. Sometimes in some lotteries, it's kind of close. And then what this friend of mine did is he just paid attention to the lottery until the amount of winnings multiplied by the chance of winning was more than the lottery ticket. But wait, let me give you a warning. That's not exactly what he did. Let me show you another lottery. It's another lottery. It's a very interesting lottery. This lottery is where you don't just win $1 million. You win like $1 trillion. It's huge. And, there will be some probability that you win it. But, with some probability, I'll say 1 over, a billion. 1 billion. This is pretty good, right? Oh, yeah, you just have to pay like $999. Does that make sense? So I have a new lottery for you. That 9 looks a little bit weird. I'll draw it again. How many of you would play this game? If somebody told you you could win $1 trillion with probability 1 over a billion, and you just need to pay $999, how many of you would want to do this? I'm a little curious. Yes, Temp ID says, on average, you're expected to earn $1 because your expected amount of winnings is actually $1,000, and you pay $999, so you end up ahead. You'll end up $1. But some people made some comments. Someone said they're too poor. You see, there's a bit of an issue here. The issue here is like, yes, sure, you'll make $1, but how much might you need to spend to get that dollar? You know what I mean? It's like, yes, sure, you're gonna win $1 on average, and your chance of winning is 1 over a billion. If somebody ever told me I have a chance of 1 in a billion of being able to do something, what I'd say is like, yeah, so you mean like practically zero, right? It's like if I see it in my entire lifetime, I would be surprised. You don't even have a billion seconds in your lifetime, I think. If I thought of, actually, I'm not sure. You might have a billion seconds. Actually, you know what? I think you do. Let's figure that out. I'm a little bit curious, but I vaguely remember calculating this while I was making the Novid app. We'll go back there. I'll go back to the billion seconds in a little bit. But about this thing, it's like, no, this is terrible. It's like along the way, you're gonna lose so many times, and you might be unlucky enough that you lose like almost 1 billion times before you finally win once, and you might need to spend $999 billion. In fact, on average, you'll actually on average spend $500 million losses, and so so you'll probably end up spending like about $500 billion before you finally go and win that one. It's awful. So I'm just showing that somehow you cannot just simply use this. So since you cannot simply use this, somebody already did it about this like billion seconds. But anyway, so this particular thing is like you cannot just use this. So what my friend did, he didn't do that. He didn't just go and take this sort of information and wait until it looked like he was ahead, because that's actually not useful either. It turned out that the lottery that he was playing in, the lottery was one where there were some smaller prizes too. So you didn't have to win the jackpot. I think it was something where you have to match a bunch of numbers. And a lot of these lotteries, you can choose your numbers, what numbers do you want to buy, and then you go and see what random numbers came out. And if you got close, and if you got some of them to match, you already win some of the money. And so actually what he did is he found a way that, because not only did the jackpot go up, all of the intermediate prizes of like matching 5 numbers instead of all 6, or matching 4 numbers, all of those prizes went up too. He was able to write a computer program to tell, like, you should just buy exactly these tickets with like these numbers on them, so that you're actually guaranteed that by putting that money in, you are guaranteed that you'll win enough of the smaller prizes to pay for all of your tickets. So this is actually what he did. It worked quite well. And unfortunately these days people change the rules of that particular game. But I'm just telling you, maybe you'll find out. And by the time when he did this, he was a college student. There's something I did. I am curious. I said this thing about 1 billion seconds. I want to know what's 1 billion seconds, just for my own understanding. So if I want to convert 1 billion seconds into years, I'm just curious. How many seconds in a year? Here's how I'll do it. I would say there are 365 days in a year approximately. Each day has 24 hours. Each hour has 3,600 seconds. So if I'm looking at this, I'm just kind of curious. What is it roughly? If I see the 365 and I see another 36, there's something I know, which is that the square root of 10 is around 3-ish. So because of that, when I see like 30-something times 30-something, I like to think that the 30-somethings multiply to 10, like the 3s-ish multiply to 10. I mean, you know, like 3 times 3 is 9, so it won't be that far off. And then to do this, I might even use scientific notation. I might say that this is like 3.65 times 10 squared times, let's leave the 24, you'll see why, and then 3.6 times 10 cubed. The reason to do this is because now I see the 3 point something and the 3 point something, and I'll multiply them, I'll call them 10 approximately. If I multiply them and call them 10 approximately, I have my 24 in front, and behind what I have is how many tens? Well, I have 6 tens. The reason I have 6 tens is because this one and this one gave me about a 10. There's 2 more tens, and then there's 3 more tens, so there's 6 tens altogether. Oh wow, it looks like there are 24 million seconds in a year. If that's the case, then, if I want to go to 1,000,000,000 seconds, I just need to do 1,000 divided by 24. So actually 1,000,000,000 seconds isn't that long. So 1,000,000,000 seconds will then be approximately 1,000 divided by 24 years. And so that 1,000 divided by 24, 24 times 4 is about 100, like 25 times 4 is 100. So this is about 40 years. Now this is not quite right. The reason this is not quite right is because I did an approximation. Over here I said like the 3.6 times 3.6. Honestly, 3.6 times 3.6, I think it might be like 12.96. And we can see, if people put the answer of exactly what is 1,000,000,000 seconds, you'll find out it'll be something. It actually might be, I don't think it's quite 40 years. And actually do please correct me if it turns out that it's not 40. I'm curious actually what the real answer is, just so we can see how good we are on our approximations. But yeah, in reality it should probably be a little bit less than 40. So because we divided by something which was too small, we should divide by more. Okay, 31 years. You're saying 31 years. I could believe that. And so when you look at all of this, you say, you know what? The statement I said was maybe false. I said like 1,000,000,000 seconds. You don't even have 1,000,000,000 seconds. You won't even see 1,000,000,000 seconds in your life. And I was like, well, actually, maybe you will. So 1,000,000,000 seconds you might actually see. Okay, what else can we do? Oh, this is cute. I saw someone ask how you win at Blockers. I don't know that game well enough. I think I've played it once or twice in my life, but it's a pretty interesting game. I just don't know exactly how to win that one yet. Somebody wants to divide by 0. Somebody said 2 divide by 0. Unfortunately, that's not defined. So you can't divide by 0 because you will get something either very, very big or very, very small, like negative small, when you divide by a number close to 0. So it's hard to say, which of those two it is. Wow, everyone's asking about games. I see people asking about the perfect strategy for Connect 4. I would say the more you can do on kind of thinking ahead to see if you can put someone into a double attack situation, which is what people have said here, that's better. And I see somebody also asked about Chinese checkers. I would put probably, actually I don't even remember how to play Chinese checkers, other than you kind of jump over stuff. So it's been a while since I played that game. I'm still looking at all of these things. Wow, it's so interesting that we see all these questions coming in. So somebody's asking, how do you win at Chopsticks? I actually don't know what is the game Chopsticks. So I think I'll have to do some research afterwards to find out what that is. I'm just going to guess it probably involves chopsticks. And apart from that, I don't know. Although it does sound to me like a kind of game that maybe are you trying to pick some things out of a structure? I'm not entirely sure. Okay. Prove pi equals 4, Eric F says. I can do that. Pi equals 4. All right, everyone who thinks that pi is anything else is just wrong. Pi is 4, and let me show you. Pi is about the circumference of a circle, right? So the way I'll do the circumference of a circle is I'll say, here's a circle. I always draw the circle first. And then I need to kind of approximate the circle. Oh yeah, what's pi? Pi is the ratio between the circumference and the diameter. So here I have a circle, and my circle's diameter is exactly 1. Now watch. I'm going to approximate the diameter of the circle by doing this. I'll approximate the circumference of the circle by doing this. I'll draw something that looks sort of like you built it in Legos. I don't know if you guys can see what I drew, but it's like it's going like a zigzag path. It's like this. It's almost like, if there was a circle and you tried to make the circle in Manhattan. I'm getting kind of lazy, but I hope you understand what I'm trying to do. Like this. Okay, I think I've achieved it. I've found something that's so close to the circle that I just need to go and figure out how long that is. And once I know how long that is, it looks like Minecraft. Oh, that's exactly what you should say. That's what I should say. It's not like it looks like Manhattan. It looks like Minecraft. So exactly, so the proof of why pi equals 4, it's called Minecraft. Just go to Minecraft and you will know. So Minecraft says that pi is equal to 4. Okay. And now, because here, watch. Now I'm going to tell you what is this length going all the way around the circle. Because if I just find out how long it is going around the circle, and I divide that by the diameter of the circle, boom, that's pi, right? So now how do I do this? I have a very complicated shape. I don't know. But let me show you a neat trick. Does anyone know what's the perimeter of this object? Can anyone tell me the perimeter of this object? Pretend that all the lines are like straight and perpendicular. Pretend they're all like vertical and horizontal and vertical and so on. You'll say this is impossible. Come on. I gave you a 3 and a 5, but there's no more information. How could you finish this? It's like, I don't know how long that thing is or that thing is. How are people saying the answer is 16 so quickly? Oh, it's because you don't need to know those numbers. You see, because if I want to know the perimeter of this thing that I just drew, you basically go and take this thing that caved in and you just bump it back out. Like this. What do I mean by bump it back out? You see this length? This vertical bit is the same length as that vertical bit. And you see the yellow part, if I bump it this way, the yellow length, sorry, not yellow length, but the horizontal part here has the same length as the horizontal part. Therefore, the perimeter of this funny blue object is the same as the perimeter of this rectangle. That's easy. The perimeter of the rectangle is length plus width, or maybe this is the length, that's the width. 5 plus 3 is 8. And then times 2, so 16. That's a trick. Now watch. Now I can figure out the perimeter of this, like, circle, the Minecraft circle. It's like this. You go deep into the Minecraft circle, and it's like it's in the zoomed in version, it looks like this. So I'm just showing you a little bit of it zoomed in. And now I'm going to use the same trick. First, I'm going to bump up this piece to there. And then I'll bump across that piece to there. Does everyone understand what I did? I took that piece and bumped it that way. And I took this piece and bumped it up. So now it's the same perimeter as what I had before. So that's good. My shape got easier. So I don't need to find the perimeter of this whole thing anymore. I just need to find the perimeter of this, where I replace with the yellow and the pink. Oh, but let's do it again. So now I'm going to go and take this particular piece and bump it across. And when I bump it across, it goes over to here. I'll also take this horizontal piece right here, and I'll bump it up. And if I push it up, it has the same length. So I get this. Let's erase this piece. Oh no! Thankfully, there's undo. Erase this piece. Okay. So now, the perimeter of the blue thing is the same as the perimeter of like the blue thing and then changing to pink, and then changing to yellow, and then going back to blue. But you can keep doing this. If I bump this piece across, then I get another pink. And now just bump this whole length up to get yellow. And do it one more time. Push that piece across. Zoop. Take this piece and bump it up. The whole length across. Zoop. And now, what I've just found out is that the perimeter of the blue thing is just as if it was like going up there. Oh no. Now people don't like what I'm doing. I'm not adding perimeter, by the way. I'm actually not adding perimeter. I'm actually just taking the things that had lengths and I was pushing them across. There's no change in perimeter. So the Minecraft version of a circle, Philip, it's not adding perimeter. What's really wrong is that it turns out that the Minecraft version of the circle was not a circle. You see, what I've just done here is I've showed that the perimeter of the blue thing, which goes in zigzags across here, is the same as the perimeter if I went across on the blue, went on the yellow, went on the pink, and then continued on the blue. Those are the same perimeter. Okay? I'm adding area, but I'm not adding perimeter. So now if I do this, if I do the same thing over here, what I find out is that actually, that thing I drew has the same perimeter as this. oh, that perimeter is just 4. That's a square, right? I mean, this is 1 across, so it's 1, 1, 1, 1. The perimeter is 4. So I just found out that I have a perimeter of 4. Okay, so unfortunately, what we've just found out is that in the Minecraft world, the perimeter is actually 4 for a circle. And that's why you don't want to say that the circle is approximately this. You see, if you look at this closely, that's not really a circle. It's doing a lot of zigzagging. I can even show you that there are other examples of things that make this happen. And the example I'll say is that there's a train that goes from my city, Pittsburgh, to Washington, D.C. And it's a little funny. If you go and take the train, trains are supposed to be fast. But if I take the train from Pittsburgh to Washington, D.C., it takes a lot longer than driving. And I once wondered, why is it that the train takes longer than driving? Now, the train is still very comfortable. It's more comfortable to me than driving because you can sleep on it, you can look out the window, it looks beautiful. And when you look out the window, you find out that what the train is doing is it's going along a river. So now if you think about what this is, the same thing happens there. The highway, by the way, doesn't go along a river. The highway just goes. So you have on the one side, you have a highway that's just going. On the other side, oh yeah, and these are Pittsburgh. And you have DC, Washington, D.C. And it just goes. Meanwhile, if you have a river, what's the river doing? Does anyone know what rivers do? They wiggle. Now, I'm not saying it definitely wiggles this much. I'm just kind of making it look more wiggly than it really is. Oh yes, I have somebody asked, do I live in Pittsburgh, Pennsylvania? Yes, I do. And greetings from Pittsburgh, Pennsylvania. That's where this live stream is coming from right now. But you see, rivers flow, and the way rivers flow is that they actually, as the river evolves over time, it starts to swing back and forth more and more, and that's because of physics. It's because as the water is coming along like one. Oh my gosh! Every time I do these motions on your screen, I need to flip. It's like being a weatherman. But anyway, as the water is going this way, right? It's like you can imagine that the water is swinging back and forth, and it's kind of pushing even more, and it's causing them to become. It's sort of causing erosion. Everywhere that the water is kinking around, it's wanting to push the stream out to go a little bit more in that direction. And so when you're going along the river, what ends up happening is, oh yes, that's hilarious. Philip Neller says it's Bob the River, and that's a callback to yesterday's Bob the Cat, where we were talking about a random cat that was randomly walking left or right. But the situation is when you have a zigzag thing here, it can actually be a longer path. It's because the zigzags are very, very inefficient. And you could imagine in the extreme case, of course that's not how it really is, it's not like that way with a river, but if it was really, really zigzagging like crazy, like this, like zigzagging like with huge zigzags, you could imagine that you ended up walking a lot more distance or riding a lot more distance. So that's why you don't use this to measure pi. Okay. Yes, oh Joshua, thank you. Thank you for making that comment about this being interesting. I mean, that to me was an eye-opener that somehow, oh, one reason why things are slow when they go along the river is because the river wiggles. Actually, does anyone know why train tracks go along the river? That's another very good reason. So trains, this is a funny thing. Like a long, long time ago, everyone used trains. And when you use trains, you try to make trains efficient. I'm not sure if you guys know this, but when you design train tracks and you want to put out train tracks, you are trying to make the train tracks be as flat as possible. In fact, the United States train network, the train track network, is one of the most advanced and most efficient ways of transporting goods in the world. Many people don't think about this. Many people say in the United States, our trains are awful. They're not on time, you can't ride them as a passenger, and it takes forever, and somehow whenever you get behind a freight train, you just go really, really slowly. But in fact, the trains are very efficient for transporting goods because you get a huge long train and it just goes. And the reason it's so efficient is because people lay out the train tracks so that they're as flat as possible. What is inefficient is if you have to go up a hill. Oh, your hill's the other way around. Yeah, you have to go up a hill and then go back down a hill. Because when you go up a hill, you have to fight your way up. When you go down the hill, you know what I mean? Like if you have a train, suppose you have a train and it's trying to go uphill, you have to actually put energy to make the train go up the hill. And you might think, well, then it's fine. Like at some point you go back down the hill. Guess what trains do if they're going down a hill? Does anyone know what a real train has to do if it's going down a hill? I'm saying that when the train's going up a hill, it has to go chug, 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 and use a lot of energy. If the train starts going down a big hill, does the train just go like, I'm gonna go as fast as I can? Yes, exactly. The brakes. It has to put on the brakes because nobody wants a train that's just barreling down this mountain, going faster and faster and faster until guess what? It falls off the tracks. So the problem is that you waste a lot of energy because these trains are designed so that you can go. The trains, by the way, are so efficient that they have so much lubrication in the wheels and like other ball bearings or whatever. They're very, very efficient. In fact, trains are the most efficient way in terms of miles per gallon of transporting goods in the United States of America. So what they do is they make it flat. Aha. That's why it goes by the river. Because the river guarantees something that's pretty flat. You see, what I'm saying is that in a mountainous area where there are mountains, you do not want to go through the effort of making your nice flat train track by digging lots of tunnels. Those are very expensive. And you don't want to go up the mountains. That's also very expensive. So instead what you do in the old days is you go find some rivers. And you go alongside the rivers. Because those rivers are pretty flat. And that's it. Okay, and indeed, I see I am speed has come back. Let's do one more question. I know that we started late today, so I'll do one more question and then we'll finish for the day. I unfortunately still have some more things I need to do right after this, still related to the COVID-19. But let's hit one more question. What can we do here? Wow. Oh, this is really interesting. It's a question about gaming. So, video gaming, I think. Sentinel asks, how do real-time games sync so well, even when players have high ping and are far away? Why do movies take so much longer to load in comparison? This is a very interesting question because I've been thinking about this, not for video games, but for Novid, for our thing that tells you whether you've been nearby anyone else who is sick with COVID-19. So the question of how do you synchronize time is a very deep one, because you may notice that in some games it's like somehow the time is all set up just right, but movies take forever to load. Some people even say like this YouTube stream that we're listening to right now, it's often like buffering or something, right? And it just seems like it's not loading. So here's the difference. In the video that you're watching, there's a huge amount of information coming. It's not just the visuals, and it's not just, it's just the visuals and the audio, although actually the visuals are most of it. A moving picture has a lot of information that's coming through. So when there's a lot of information coming through, then it's not as efficient. You have to actually spend more effort to get all that information through. On the other hand, in a video game, you're not actually having to send to the other person who you're playing the game with. You don't have to send them a complete colorful picture with all the details of your game. Instead, what a video game designer has to do is they need to figure out a way so that all of the important information can be sent across. So in fact, there's a transmission of information, which is not that much information. It's just like your thing that was over there has moved over to there. So it's very different from this kind of a video because YouTube doesn't know what you're watching. Like suppose suddenly my studio were to completely change and I'm suddenly wearing a green shirt. YouTube has to be able to do that. Sorry, anyone who's hoping that was going to happen, that didn't happen. But in any case, it's like somehow the video game doesn't have to do that, and the game designer tries to transmit as little information as they can. The next piece, though, is how do they synchronize the clocks? The way that you synchronize the clocks in computers is you actually have some servers, you have some computers in the world which help to provide the time. And then what these computers do is they send signals, like your computer, if you want to synchronize clock, will keep sending signals to these clock computers, which are out on the internet. And there are actually many different layers of clock computers. And ultimately, you try to contact the one that's closest to you to go and try to find out, what is the time. For example, here's one easy way. If I go ask the clock computer and I find out what time it is, I don't exactly know how long it took my signal to get there and back. Suppose I go and ask the clock, hey, what time it is? What time is it? And a little bit later, the clock says, it is 4 o'clock p.m. and 35 seconds. I cannot just go and say it's 4 o'clock p.m. and 35 seconds, because I don't know how long it took that message from the clock to get to me. So what would I do? I would ask it twice. Actually, these things are more sophisticated than what I'm saying, but I'm just giving a simple example. If I go and ask the clock, hey, what time is it? And it says 4 minutes and 35 seconds. As soon as I get that back, I immediately ask again, hey, what time is it? And it says 4 minutes and 39 seconds. Aha. Then I'm going to guess that, like I asked, what time is it? Well, let me draw a picture. That's probably the easiest way. Okay? So here's what's going on in time. So I have my own clock on my own computer. Okay? So I have my clock. And then I have like the time clock, like the server, the clock server. Now my clock is like possibly a little bit off. For example, suppose my clock says it is 4 o'clock. And how many seconds? I don't know, 27 seconds, something like that. At that exact moment, I go and ask a question. I go and say, hey, what time is it? And I don't know how long it takes for my thing to get across, but somehow the clock server responds. And the clock server responds, and the message that comes back from the clock server is, well, at the time that I responded, it was 4 minutes and 35 seconds. I just said, I think I might have said 37 before, let's just say 35. And at the moment that I get that message, I find out that, oh, I see, it is 4 o'clock and 29 seconds. So if I do something like this, what would you say? Should you go and say that, aha, my clock then it was 35 in reality, my clock says 29. Is it correct for me to say that my clock is exactly 6 seconds too slow? Actually, no. So I'm not exactly 6 seconds too slow because I don't know when that clock sent the measurement, right? The clock sends the measurement and it sends its measurement exactly it tells you what time it is, but at the time it's sent. So actually when it's sent, at that time over there in the clock server, it was 4 o'clock and 35 seconds. So at 4 o'clock and 35 seconds, it sent this message to you. And you see that it's 4 o'clock and 29 seconds when you get it. And you get a message saying 4 o'clock and 35 seconds. But that does not mean that your clock is 6 seconds too slow. You see, because somehow, if you look at what's going on here, it took some time for it to get there and back. So one thing that's often used is it's often used that you take the average of these two and you say, well, probably when the clock server said 4 o'clock and 35, probably for me, that was halfway in between, 4 o'clock and 28. And I'll say then, my 4 o'clock and 28 is the clock server's 4 o'clock and 35. So I'm actually 7 seconds slow. Did that make sense? So that's actually what you would do to solve this kind of a problem. And I said something about sending it multiple times. If you send it more times, you can take an average and hopefully be even more accurate. But these questions about, how would you try to synchronize clocks are very interesting because if you want to synchronize clocks closely enough to play a video game, you need to be very, very precise. Okay, great. So unfortunately, today's live stream has to come to an end. I'm glad that everyone stayed on. Thank you very much for coming, even though I was a little bit late coming in at the beginning. If you liked what you saw, what will help me to keep this decision, to keep running these live streams, is if you tell more people to join. I really do choose what to do with my life based on what will have the most positive impact. And the way we measure positive impact is with this number right here, which is like how many people are coming. I saw that we have more people than usual, both yesterday and today, which is great. And let's try to keep that up. See you all next time, and have a great day.